Alright, let's go. Number 10. The Arrow of Time. In 1927, Arthur Eddington was writing a book for the general public, a collection of essays later published under the title The Nature of the Physical World, aimed at readers with no equations. Somewhere in the middle of the manuscript, he needed a phrase for something that had bothered physicists for 2 generations and had no name. Every fundamental law of physics known at the time was time-symmetric. Newton's equations of motion, Maxwell's equations of electromagnetism, Schrödinger's wave equation for quantum mechanics, film a set of colliding billiard balls, then play the reel in reverse, and the reversed motion satisfies Newton's laws exactly. The equations do not distinguish forward from backward. Time, in the mathematics, is a coordinate with no preferred direction. But you remember yesterday. You do not remember tomorrow. Cups shatter. They do not unshatter. The universe you inhabit has a direction, and the laws that govern it do not. Eddington gave the mismatch a name. He called it the Arrow of Time. Eddington's proposed answer was entropy, the second law of thermodynamics, which states that in closed systems, disorder tends to increase. He identified this statistical tendency as the source of time's apparent direction. But Ludwig Boltzmann, decades earlier, had already shown that entropy is not a fundamental law in the way gravity is a law. It is a probability. Nothing in physics forbids a shattered cup from spontaneously reassembling on the floor. The process is only astronomically unlikely. That unlikeliness needed its own explanation, and this is where the problem metastasized. Roger Penrose has spent the last 40 years pointing out that the low entropy starting condition of the early universe is itself unaccounted for. The initial state is exquisitely fine, tuned in a direction the physics does not require. Sean Carroll has proposed multiverse selection. Julian Barbour has argued time is an illusion of relational geometry. Boltzmann brain arguments generate infinite absurd observers who would statistically outnumber real ones. Every proposed resolution shifts the mystery further upstream or breaks something else on its way. Every memory locked inside your skull exists because entropy pointed one direction rather than the other. Every choice you have ever made was made moving forward through a landscape you did not select. Your grief for people you have lost exists because you cannot walk back. The direction was set before you were. What makes the past different from the future? When the equations say they should be indistinguishable, the direction problem has a partner in particle physics. Number 9. The Kion asymmetry. James Cronin and Val Fitch traveled to Brookhaven National Laboratory in New York in 1963 with a routine goal. Their experiment was designed to confirm something nobody expected to be interesting: that a class of subatomic particles called neutral kaons decayed in a strictly symmetric way. The prediction had been in textbooks for years. They were checking a decimal place. The symmetry was called CP charge conjugation combined with parity inversion. Swap a particle for its antiparticle, mirror flip its spatial coordinates. And the resulting physics was believed to be identical to the original. Under this rule, one particular decay mode of the neutral kaon, a decay into 2 pions, was forbidden. The particle should have decayed only into 3 pion final states. Cronin and Fitch built the apparatus to verify this. They found the 2 pion decay. It was rare. It was persistent. It was unmistakable. Roughly 1 kaon in every 500 did exactly what the theory had ruled impossible. Their result appeared in Physical Review letters in July 1964. The measured asymmetry was 210.3, 2 parts per thousand. The universe, at the level of particle physics, distinguishes between matter and antimatter, and, by extension of the CP theorem, between the forward and backward flow of time. Cronin and Fitch shared the Nobel Prize in Physics in 1980. In 1998, the C-Clear experiment at CERN confirmed direct time reversal violation in the same kaon system. The size of the asymmetry is what turned the discovery from a curiosity into a wound. Andrei Sakharov, in a 1967 paper, argued that some form of this violation was required to explain why the observable universe contains matter at all. A perfectly symmetric Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other completely. but the kaon asymmetry is far too small, by a factor of roughly 10 billion. To account for the matter that survived, physicists have hunted additional sources of CP violation in B-meson decays at Baybar and Bell. They have looked in the neutrino sector. They have searched in the strong nuclear force. Nothing found so far is anywhere near large enough. Every atom in your body exists because, in the first fraction of a second after the Big Bang, matter beat antimatter by a razor-thin margin. A tiny surplus of matter escaped mutual annihilation. You are that surplus. The reason it happened remains missing, and the only concrete measurement of temporal asymmetry sits inside a decay rate that fails to explain your existence by 10 orders of magnitude. Why does the universe distinguish forward from backward? And why by exactly this uncomfortable margin? Some symmetry violations are small. The next one is enormous. Number 8. The Gödel universe. Kurt Gödel had already destroyed the foundations of mathematics with his incompleteness theorems. In 1949, he turned his attention to Einstein. He was preparing a contribution for a volume celebrating Einstein's 70th birthday. And he was living in Princeton, close enough to Einstein to walk with him and argue. He decided to look for exact solutions to Einstein's field equations that no one had noticed. General relativity at the time was understood as a theory of local geometry. Mass and energy curve space-time. Particles follow the curves. The equations describe how space-time bends in the presence of matter. But the global structure of the solutions had barely been mapped. Physicists assumed the equations respected causality, that the past was the past and could not be revisited. It was an assumption, not a theorem. Gödel found a counterexample. He constructed an exact solution to Einstein's equations describing a rotating universe. Inside it, closed time-like curves existed everywhere. You could take a path through space-time that returned to its own past, without ever exceeding the speed of light. The paper appeared in Reviews of Modern Physics in July 1949. Einstein wrote a response in the same volume. He acknowledged that Gödel's solution was mathematically valid. He said it disturbed him. The disturbance was legitimate. The equations Einstein had built to describe gravity contained, buried in their global structure, permission for time travel. Nothing in the mathematics ruled it out. Physicists have been trying to close the loophole ever since. Stephen Hawking proposed the chronology protection conjecture in 1992. Arguing that quantum effects near A would be time machine should generate infinite vacuum energy and destroy the machine before it forms. Kip Thorne, working on wormhole solutions, ran into the same divergences. The Kachi horizon, the boundary where the past becomes ambiguous, appears mathematically unstable in every model tested. But no proof exists. The Gödel universe requires the observable universe to be rotating, which measurements of the cosmic microwave background rule out to high precision. It does not rule out other closed time-like curve geometries. The Kerr solution for rotating black holes contains them. Certain wormhole geometries contain them. The traversable variants remain mathematically consistent within general relativity. Awaiting a proof that physics forbids what the mathematics permits. Somewhere in the equations that describe the gravity holding you to your chair, there is a set of solutions in which you could visit your grandfather. General relativity does not tell you that you cannot. It only refuses to say why. What law forbids the paths the mathematics allows? Gödel found the paths. Quantum mechanics may have found the resolution. Number 7. The Deutsch resolution. David Deutsch, at the University of Oxford in 1991, was working on the foundations of quantum computing when he decided to apply the tools of quantum mechanics to closed time-like curves. The classical version of the problem had been unresolved for half a century. If you travel back in time and shoot your grandfather before your parent is conceived, you cannot exist to make the trip, which means you did not shoot him, which means you do exist, and the logic runs in a circle with no exit. The classical framework offered no way out. Igor Novikov, in the Soviet Union during the 1980s, had proposed the self-consistency principle. Only histories that formed consistent loops could actually occur. A time traveler who tried to shoot her grandfather would find the gun jamming, her aim faltering, the bullet ricocheting. The universe would conspire to prevent inconsistency. It preserved causality, but at the cost of what looked like teleology. The universe would seem to be arranging events on purpose. Deutsch found a different exit. Using the many worlds interpretation of quantum mechanics, he showed that closed time-like curves could be consistent with quantum theory if the traveler emerges into a branch of reality slightly different from the one she left. His paper appeared in Physical Review D, Volume 44, in November 1991. The mathematical result was clean. Quantum mechanics on a closed time-like curve requires only that the density matrix of the traveler match itself after one loop. This condition is satisfied even when the traveler alters classical events, as long as the alteration branches history rather than overwriting it. The traveler kills a grandfather. She returns to a universe where that grandfather died. Her own grandfather, in her originating branch, is still alive. Consistency is preserved. Paradox dissolves. The failures of this resolution began appearing quickly. Seth Lloyd and colleagues at MIT proposed a competing framework, the post-selected model, that produced different predictions in principle. Scott Aaronson showed that Deutsch's closed time-like curves would collapse the distinction between quantum and classical computation, making some intractable problems trivially solvable, which suggests either the model is wrong or computation is stranger than anyone thought. Firewall paradoxes and unitarity concerns have proliferated. Every proposed physical implementation runs into a different wall. If Deutsch is right, you can visit the past. You cannot visit your past. The past you would find would belong to someone who looked like you, but whose fingerprints, memories, and small scars would drift away from yours the moment you arrived. You could kill a grandfather. He would not be your grandfather anymore by the time you pulled the trigger. If you can only touch alternate pasts, have you traveled in time at all, or only walked sideways into another life? If your past is untouchable, what does that make your future? Number 6. The block universe. Einstein spent the last months of his life corresponding with the family of his oldest friend, Michel Besso. Besso had died in Geneva in March 1955, weeks before Einstein himself. In the condolence letter, Einstein wrote a line that has since been quoted more than any of his equations. He wrote that for physicists like himself, the distinction between past, present, and future was only a stubbornly persistent illusion. He meant it precisely. Special Relativity, which he had published 50 years earlier, had already dismantled the classical notion of universal time. If two events are simultaneous for one observer, they are not simultaneous for another observer moving relative to the first. There is no shared now. Different observers slice space-time into moments in different orientations, like different diagonal cuts through a loaf of bread. If any slicing is as valid as any other, then every moment must exist in the loaf. The past is still there. The future is already there. Philosophers call this view eternalism, or the block universe. In it, time is a dimension, and all points along it are equally real. The philosophical response arrived in 1966. Cornelis Reitdijk, a Dutch philosopher of science, published a paper in Philosophy of Science arguing that special relativity logically implied determinism. Hilary Putnam extended the argument the following year in the Journal of Philosophy. The reasoning, now called the Reitdijk-Putnam argument, ran on the geometry alone. If someone in relative motion has your future in their present, then your future is as fixed as your past. Free will, in the sense of open possibility, becomes impossible. Philosophers have not accepted this quietly. Growing block theorists argue that only the past and present exist, and the future is added moment by moment. Presentists argue that only the present exists, which requires special relativity to be wrong about simultaneity, and physicists are unwilling to give it up. The A theory and B theory of time, dating back to J.M.E., McTaggart's 1908 paper, In Mind, remain unresolved after more than a century of philosophical work. Physicists mostly ignore the debate. Their equations do not need a moving present, and adding one has never improved a prediction. Somewhere along the four-dimensional block that contains your life, the moment you die already exists. It is not waiting to happen. It has coordinates. The feeling of moving through time, the sensation of possibility opening in front of you and closing behind, these would be perceptions of a traveler walking through a landscape that is finished, painted, hung. What is choosing, exactly, when every choice you will ever make is already sitting at a specific space-time coordinate? Physics has a limit on how far back into time it can even see. Number 5. The Planck time wall. Before general relativity, before quantum mechanics, before nearly everything modern physics is built on, Max Planck was working on a problem that seemed almost aesthetic. He wanted to construct a system of units, a system of measuring length, time, mass, and energy that did not depend on anything human. No meters based on the Earth's meridian. No seconds based on the Earth's rotation. He wanted units built only from the fundamental constants of physics. In 1899, he assembled them from 3 constants: the speed of light, Newton's gravitational constant, and what would later be named after him, Planck's constant. From these, dimensional analysis gave him a length, a time, and a mass, the natural units of the universe. The Planck time came out to 5.391044 seconds. Planck himself did not know what it meant. He suspected it was fundamental. He did not know why. Modern physics has an answer, and the answer is a wall. Below the Planck time, the fabric of space-time itself becomes uncertain. Quantum gravity effects, the effects that would arise from combining general relativity and quantum mechanics into a single theory, which physics has never successfully done, dominate at Planck scales. Time, at those scales, can no longer be treated as a smooth parameter. The concept fluctuates. Space-time may foam, tear, connect, and disconnect. The question of whether one event happens before or after another may not have a definite answer. Multiple approaches have tried to describe what happens on the other side of that wall. String theory reformulates space-time as vibrations of fundamental strings, but requires extra dimensions no one has observed. Loop quantum gravity discretizes space-time into finite loops, producing a picture in which time is granular but leaving many predictions untested. Causal dynamical triangulation builds space-time from small triangular pieces and has produced suggestive results but no experimental confirmation. Emergent gravity models propose that space-time is not fundamental at all, but a large-scale effect of something deeper. Every approach is mathematically self-consistent. No two agree. None have been tested at Planck scales, because reaching those scales would require an accelerator larger than the solar system. The first 10 and 44 seconds of the universe you live in, of the process that produced the atoms currently making up your bones, that interval sits behind a wall physics cannot see through. Whether time existed before the Big Bang, whether before is even a meaningful preposition to apply to that boundary, is a question no experiment has ever been able to touch. What was there before there was a before for anything to be before? Below the wall is one mystery. Above it, personal time gets stranger. Number 4. The Hoff-LA-Keating result. Joseph Hafele, a physicist at Washington University in St. Louis, and Richard Keating, an astronomer at the U.S. Naval Observatory, boarded a series of commercial airliners in October 1971 with 4 cesium beam atomic clocks. Their itinerary was ordinary. They flew twice around the world, once eastward, once westward, using standard commercial flights. The passengers around them were reading newspapers. The clocks in Hafele's carry-on were checking whether Einstein was right. Newtonian physics predicts that a clock is a clock. Time is universal. A watch on an airplane and a watch on the ground, if calibrated identically at takeoff, will read identically at landing, regardless of what happens during the flight. This was the intuitive, common-sense view of time held for over 2 centuries. It was still the view most non-physicists held in 1971. It was still the view many physicists tacitly assumed applied to velocities lower than a significant fraction of the speed of light. The clocks disagreed. When Hafele and Keating landed and compared their airborne clocks with the reference clocks at the Naval Observatory, the readings differed. Not by a random amount, by exactly the amount predicted by combining special and general relativity. Their results were published in Science in July 1972 in 2 companion papers. The eastward flying clocks lost 59 nanoseconds relative to the reference clocks. The westward flying clocks gained 273 nanoseconds. The predictions from Relativity, accounting for both the velocity of the aircraft, special relativistic time dilation, and the higher altitude weakening the gravitational field. General relativistic time dilation matched the measurements within the experimental error bars. Einstein's 1905 and 1915 theories were confirmed at velocities anyone could achieve for the price of a plane ticket. There is no failed explanation here. The result has been reproduced hundreds of times, most consequentially in the GPE satellite network, whose clocks would drift by kilometers of positional error per day if relativistic corrections were not built into the software. But the interpretation is where physicists still argue. Which twin is younger when both were in relative motion? What is really happening? Presentist accounts of time cannot cleanly accommodate the result. The block universe view can, but only by giving up an open future. Relational accounts propose there is no fact of the matter about absolute simultaneity, only about who met when. Every long flight you have ever taken has aged you slightly less than the people who stayed on the ground. The effect is real, cumulative, and measured. You are not the same age as the twin who never travels. Nobody is. If there is no universal clock, who is right about when things really happened? Personal time is strange. Universal time may not exist at all. Number 3. The Wheeler-DeWitt problem. Bryce DeWitt was trying to quantize gravity. In 1967, from his office at the University of North Carolina, he was making one of the most serious attempts anyone had made at the great unfinished business of 20th century physics. Taking general relativity, which describes gravity, and rewriting it in the language of quantum mechanics, which describes everything else. He was working from ideas he had developed with John Wheeler at Princeton, and the equation he was constructing was going to bear both their names. The Schrödinger equation, the central equation of quantum mechanics, describes how a system's wave function evolves through time. It has a time variable in it, the letter t appearing explicitly, driving the evolution of every quantum system ever measured. Time, in quantum mechanics as it was known, was the parameter along which change happened. Without a time variable, the equation would be static. Nothing would ever change. DeWitt derived his equation. It appeared in Physical Review, Volume 160, in August 1967. The time variable was gone. The Wheeler-DeWitt equation is the leading candidate for the fundamental equation of quantum cosmology, the equation governing the wave function of the entire universe. In its standard form, the equation has no time. It reads, in effect, that the wave function of the universe does not evolve. The universe, at the fundamental quantum gravitational level, is frozen. This result is known in the field as the problem of time, and it has been unresolved for nearly 60 years. Multiple proposed solutions circulate. Don Page and William Wooters in Physical Review D in 1983 proposed that time is an emergent property of entanglement. A subsystem entangled with the rest of the universe experiences change relative to that entanglement, while the total universe remains static. Carlo Rovelli, working in loop quantum gravity, developed related ideas of thermal and relational time. Julian Barber has argued that time simply does not exist. What we call time is only the ordering of configurations. Carol Kuchar cataloged the technical failures of each proposal, one by one. No consensus exists. The equation supposed to describe reality most deeply says reality does not change, and no one has explained why we experience it as changing. If Page and Wooters are right, your experience of the passage of time is a consequence of your entanglement with everything else. A completely isolated system, cut off from every particle in the universe, would not experience time. The pulse you feel in your chest ticks along with your entanglement to everything around it. What is passing when the equations say nothing is? If time is emergent, black holes are where the emergence fractures. Number 2, the black hole contradiction. In 1939, J. Robert Oppenheimer and his student Hartland Snyder published a 9-page paper in Physical Review titled On Continued Gravitational Contraction. They were tracing what happens when a massive star collapses under its own gravity with no force to stop it. The calculation had never been done in full. They did it. The paper contains the first modern description of a black hole, and it contains, buried in its equations, the seed of a paradox that physics still cannot resolve. Their calculation described the collapse from two perspectives. The first was the perspective of an observer falling inward with the collapsing matter. The second was the perspective of an observer watching from outside. At a safe distance, general relativity gave definite predictions for both, and the predictions did not match. To the falling observer, the collapse proceeds smoothly. The star contracts. The infalling matter passes through what will become the event horizon in a finite amount of the falling observer's proper time. Nothing dramatic marks the crossing from the inside. To the outside observer, the same fall never completes. As matter approaches the event horizon, gravitational time dilation grows without limit. The infalling matter appears to slow. Its light redshifts towards zero frequency, fading to invisibility. The horizon appears to freeze the fall indefinitely for the entire remaining age of the universe. Both descriptions are correct in general relativity. Both are mutually contradictory. Oppenheimer noted the disagreement without resolving it. The tension became sharper in 1975, when Stephen Hawking published in Communications in Mathematical Physics his result that black holes emit thermal radiation and slowly evaporate. It became sharper still in the 2000s, when the black hole information paradox forced physicists to ask what happens to information carried by matter that has both crossed the horizon in finite proper time and never crossed the horizon in outside coordinate time. Multiple frameworks have been proposed. Leonard Susskind's black hole complementarity in the 1990s argued that the two descriptions are separately valid and never in contact, so the contradiction never manifests to a single observer. The AMPS firewall argument in 2012 by Almheri, Marolf, Polchinski, and Sully showed that complementarity conflicted with quantum mechanics unless you were willing to accept a wall of high-energy particles at the horizon. The ER/EPR conjecture, proposed by Maldacena and Susskind in 2013, tried to unify quantum entanglement with wormhole geometry. No proposal has been confirmed. No consensus has formed. The contradiction Oppenheimer noticed in 1939 is still, in 2026, unresolved, somewhere in the sky. Right now, something is falling into a black hole. From that observer's perspective, the fall completes. From ours, it never will. Which description is real? That was time at the edge of the universe. This is time inside your skull. Number 1. The present moment. A 26-year-old patent clerk in Bern, Switzerland submitted a paper to the journal Annalen der Physik in June 1905. Its title translated as On the Electrodynamics of Moving Bodies. The paper's opening section is what changed physics. In that section, Albert Einstein defined what it means for two distant events to happen at the same time. He did it by imagining light signals synchronizing clocks across a distance. His definition looked innocuous. It was not. The Newtonian view of time, held for 2 centuries, treated simultaneity as absolute. If two events happen at the same instant, they happen at the same instant for everyone. The universe possesses a global clock. Every observer, everywhere, agrees on what now contains. It was the framework built into common sense, into philosophy, into every prior physical theory. Einstein showed that simultaneity depends on the observer. Two events occurring at the same time for a stationary observer occur at different times for an observer in relative motion. There is no shared present. The consequence has never been undone. Every experimental test of special relativity, from Michelson-Morley through the CERN-muon experiments through Hoeffel-Keating, through modern optical clock comparisons, has confirmed the relativity of simultaneity. What one observer places in their present, another places in their past or future. There is no privileged slicing of space-time into moments. The word now refers only to a local construction, one built inside a single nervous system, from signals limited by the speed of nerve conduction, not the speed of light. Every attempt to rescue a universal present has failed. Neo-Lorentzian theories try to reintroduce a preferred rest frame, they add unmeasurable structure without changing predictions, and physicists reject them by Occam's razor. Presentist philosophers argue only the present exists. Relativity forbids specifying which present. Growing block theorists say only the past and present exist. They still cannot answer whose present grows. Every attempt to save the intuitive notion of now fails at the same point. No experiment can locate it. The moment you experience as now is a construction inside your skull, assembled from photons that reached your retina several dozen milliseconds ago, processed by neurons firing at the speed of sodium ions crossing membranes. The signal from your fingertip touching a surface arrives at your brain 30 to 40 milliseconds after the touch. Your brain edits these delayed signals into a coherent scene and presents it to consciousness as the present. The moment your body actually inhabited has already passed by the time your brain has finished building the report. You have never once in your entire life experienced the present, only the recently completed past dressed up as now. Every entry on this list sits at the center of physics, not at the edges of its ignorance. The arrow of time is embedded in thermodynamics. The kaon asymmetry is embedded in the Standard Model. The block universe is embedded in Einstein's most confirmed equations. These are not gaps in our knowledge waiting to be filled. They are shapes at the heart of our best tested theories, quietly refusing to resolve. The universe is not confused about time. We are. And the confusion is not decreasing. If you want to see more videos like this, click the video on screen now.